I don't remember. So D and D2 and D3. This is defined in the book of Evans. So that's why there is a particular name, but I don't remember the name. Do you, Camilo, do you remember what we call it? D2 and D3?
No, sorry, I don't.
Okay. So this was the way. So basically, this L is see L U equals to summation of. So this L is an operator, and this L is nothing but A 1x D plus A 2x D 2 plus dot 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 plus A and x B of M. So can you see that? And as soon as you apply this on the operator U, so it becomes this. So I am explaining this. So this L operator is the combination of the derivatives, the linear combination of the derivatives. Is not it? Mth order derivative till the mth order. So is it clear what is this L? L is an operator. If what you call it, it is called as the derivative operator. Is not it? This one. Are you guys available here? Isn't it? It is a derivative operator. Del over del x is a derivative operator. Their linear combination is going to be derivative operator.
Yeah.
Yes.
So in the same way, the second order is coming. So this L is the combination of the derivative operator. Is not it? So now you have the definition of this L. We are going to proceed with the adjoint and the weak solution of this mth order linear partial differential equation. So basically, behind studying these topics, we basically are interested in Duhamel's principle, which we are going to study in the weak solution in the heat equation, and then we will be coming on the fundamental solution in the wave equation, basically to define the Green's function and to the Poisson kernel and to the Perron's method. So that's why today lecture is not like it is exact your syllabus, but all the theory which I am defining here, like adjoint, weak solution, fundamental solution, kernel. So this is going to define the Green's function, Poisson kernel. So it is very necessary, for the further study. So that's why I'm doing so. So this is a very basic. You already know what is adjoint. You already know what is weak solution. You already know what is a Heaviside function. So this is the thing which we are going to discuss. So let omega is a domain in n-dimensional space, and suppose this is a bounded domain with piecewise C1 boundary, means the function which is defined in this domain is defined on the boundary whose first order derivative is continuous. So the divergence theorem holds. So the divergence theorem holds. So basically this is the requirement of the divergence theorem, because the Gauss divergence theorem is a very powerful technique to connect the volume integral to the surface integral. So when we are talking about the domain, so the domain is the volume, and we are talking about also the boundary. So the boundary is the surface. If we are in n-dimensional space, so the surface will be n minus 1 hypersurface, and the domain will be the n integral, and the surface will be n minus 1 integral. So basically, when we are in n-dimensional space for volume, we simply write it is like omega. Like in n-dimension, we cannot like the integral like dot dot dot. Some people like write it, but we are not going to do that. We will simply write this omega d of v, and then for the, this is just a notation. We already know about the notation in our previous classes, so I think that you guys are aware of those things and you have studied those topics. And for the surface, we are going to write like this. So every time when this integral is coming with del omega in n-dimensional space, so this is n minus 1 integral, keep in your mind. And when this integral is coming with the domain, so this is n integral, and this dv is like dx1 dx2 dot 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 dxn. So please keep this thing in mind. This is very important from the notation perspective. In the Evans book, at the very last page, they are giving 8 to 10 pages just for the notation. So that's, you don't need to go over there, because every time I already define the notation. So divergence theorem hold. Now I already have uploaded the notes, so you guys don't need to worry about the notes. As a consequence, if we are taking two functions which are omega dash, so omega dash is omega union delta omega. So u and v are two functions which are piecewise, which are differentiable, and its first order derivatives are continuous, because these u and v are belonging to C1. So now the integration of del u over del xk v ds. Do you guys know the integration of two function? Would you please tell me integration of the product of two function? You don't know integration of a dot b dx equals to, if this is first function, this is second function.
It's the integration by parts.
Yeah, exactly. That's what I am going to do here. But before that, you need to know. So this is the integration of the product of two function. So which we are going to use this thing. So this will be like, take v as a function, first function, and take this as a second function. Then integration v, and the integration of the derivative is the same function u dx on the domain minus integration. The derivative of this function will be del v over del xk, and again the integration of this will be u d of x. Now this is a volume integral, this is a volume integral. This dx, you know what is this? dx1 dx2 comma dot 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 dxn, because we are in the volume, we are in n-dimensional space. So now using the Gauss divergence theorem, this can be written as integration from v u or uv, whatever you want to write, the normal at that surface d of s, and this will be delta. Just to ignore the confusion, I am writing it in minus. Okay, so if we are considering that either u or v, this is the integration at the boundary. So if we are considering that either u or v vanishes at the boundary, so what will be the value of this integration? If
0.
0, exactly. So if we are assuming that either u or v vanishes at the boundary, so this integral will be 0. So nu k is the kth component of the exterior unit normal. That is basically we are using to write the using Gauss. I have written the notes, but in your notes, each and every step is not like I haven't written I am using Gauss divergence theorem, so you need to take the class from where this is coming and from where this is not coming. Okay, so nu is the component of the exterior unit normal that is basically used in the Gauss divergence theorem. In particular, suppose either V or U vanishes on the boundary, then the integral will be 0 and we are left with integration omega del u over del xk v dx is equals to minus del v over del xk u dv. Now you guys can see that if we are assuming that either v or u vanishes on the boundary omega, then we don't need to consider we don't need the necessity of u belonging to this C1. It is not required because the derivative is disappear. So this equation, say it is equation number second. Equation second holds for u belonging to C1 omega and v belonging to C01 omega. Again, just repeat this integral. Again, when you will repeat this integral, this will be coming like minus 1 into minus 1 integration del 2 v over del x k square u d of x. Is it clear? Can you write this for the second derivative using the same procedure? U and v are vanishes at the boundary. So in the same way, if we go for the mth order derivative, because I have taken here this L operator is basically the combination of the derivative function, the combination of the derivative operator till the mth order. See, for the first minus 1 to the power 1 came, for the second minus 1 to the power 2 is coming. So for the mth order derivative minus 1 to the power m will be coming and we are left with u d alpha v dx. For all u belonging to the space of the mth order differentiable function and v is belonging to the. So if we replace this with the L operator, so it can be written as where this L dash V is defined as minus 1 to the power m and just put summation modulus of alpha is varying from m minus 1 to the power modulus of alpha d alpha a alpha x v. Is it clear? This L dash is a derivative, but since we say this minus 1 to the power m inside this, so this L dash is not exactly L, but this is coming with minus 1 to the power alpha. Is it clear? How this L dash is coming? Was this L clear to you or not? This operator L.
Yes, but you can repeat the last thing that you say, please.
So I said that this L operator was the combination of the summation of the mth order derivative of mth order derivative operator, like del over del t plus del over del x dx over dt. So in the same way, when this derivative is passing under this kind of integration, like when we are applying the integration on the product of two functions, what is happening? That this derivative is passing to the second function, is not it with the negative sign. This derivative is passing to the second function with the negative sign under the condition when either both of the functions vanishes on the boundary. So what is happening? This derivative is passing to the second function with the negative sign. At every integration, we are getting one negative sign, is not it? So if we are on the mth order derivative, we are passing the mth order derivative to the another function, then we are getting minus 1 to the power m, and this d alpha v can be written as L of v. Is not it?
Yeah.
So, sorry. So basically what I am saying that here I defined L in this way. How I am defining L dash? I am defining L dash minus 1 to the power modulus of alpha, summation mod of alpha where is less than or equals to this d of alpha. Now this a alpha is coming inside that derivative. So what is happening? Because let me explain this thing on the second order derivative function. Suppose we have a naught x del 2 u over del x square plus a1 x del 2 u over del t square equals to 0. Now I am taking so what will happen, and I am also assuming that either u or v vanishes on the boundary. So this integral will be like this: u del 2 over del x square a naught x v plus integration u del 2 over del t square a1 x v d of x omega omega d of x. Why it is coming? Because we are taking the integration of the two product function del 2u over del x square and v. Now this a naught x is combined with this v and making it a unique function. Since v is vanishing, so this whole function, suppose this is v. So basically I am writing it like omega. This is v1 del 2 u over del x square v1 dx plus integration omega del 2 u over del t square v2 dx. So this second order derivative will pass to the second function like at v1 according to this theory, when we are assuming that either both of the function vanishes on the boundary. So this is this. Now here the L operator was defined as a naught x del 2 over del x square plus a1 x del 2 over del t square. However here the L operator is defined as L dash del 2 over del x square A naught x L V plus del 2 over del t square A1 x and V. Is it clear how this operator is defined? Or shall I explain it again? Is it clear?
Yeah.
So this L dash operator is defined now. Since this was a second order derivative. So that's why minus 1 to the power 2 minus 1 to the power 2, that will be a single plus 1. So that's why I am not writing. However, if it was first order derivative, then minus was going to appear according to this transformation of the derivative on the second function. So the L dash operator is defined as summation modulus of alpha is less than or equals to m minus 1 to the power modulus of alpha d alpha a alpha s v. So I have written in a very clear way. Here in the class I am writing in a very, so L dash V equals to this operator. This operator is known as, this operator L dash, the operator L dash is called the adjoint of L and is an mth order linear differential operator. And also to define this operator, what is the necessity is needed, that if we are in the mth order linear partial differential equation, then these coefficients a0 and a1 should be mth order continuous for mth order differentiable function. Then we can apply this derivative on this one. So if it is a second order linear partial differential equation, so the coefficient of that second order linear partial differential equation should be second order differentiable. So that's why in the very first week I wrote a alpha x is a real valued function, and usually we take a alpha should belongs to the space of the modulus of alpha order differentiable function. So because I was going to define the adjoint operator and the adjoint operator is needed, the necessity that these coefficients should be mth order differentiable function. So that's why this is belonging to the class of C modulus of alpha function. Since here it is a second, here it was second order, so this should belong to the C2. So this operator L dash is called the adjoint of L and is an nth order linear differential operator. Now if U satisfies, if you have any small doubts, then please do ask. Omega, then integration U L dash V is equals to integration of omega F, because again using the same theory we can write L of U into V d of x in the omega, and L of U is defined as V F. Holds for this V that is belonging to the class of C naught M omega. Now under this integral, we know that either U or V, we don't need to have its mth order derivative to be continuous, mth order derivative to be differentiable, because these derivatives are appearing inside the integration. So as soon as it will have a discontinuity, we will break the integral. So what is the condition is required? Only U and F need to be integrable. Grable on compact subsets of omega, because omega was a bounded set, and when we are taking any closed subset of this omega, then that is going to be compact set. Any closed subset of a bounded set omega that is contained in Rn. Is it compact or not? Suppose this closed set is set D. Any closed subset of a bounded set omega where
In Rn, it's correct by the Heine-Borel theorem.
Heine-Borel theorem, yeah. Like actually, I am not including a lot of functional or major theory. It is very easy to write it in this way, because even we can analyze, suppose n equals to 1 and you are taking a domain of an interval that is a bounded interval. So every time when you are taking a closed subset of that bounded interval, that is going to be compact, because every closed and bounded set in R is compact. So every closed and bounded set in Rn is going to be compact. So that's what I'm taking just. That U and F belongs to L local 1 omega, and this defines that U belonging to this to be a weak solution of L of U equals to N if equation 6 holds for every V belonging to C naught and omega in particular if L equals to del over del xk and U is a weak solution of del U over del xk equals to F, then we say F is the weak derivative of U. So remember this definition when we call it a weak derivative. So every time when we are going to define a weak derivative, it will not be defined automatically. It will be defined in the term of the integration. So F will be called a weak derivative of U when this integral quantity is satisfied. So this is weak derivative, which we are going to use the definition. Just I have a question for all of you. This L is a wave operator in 2 dimension. So if I am assuming that the independent variables are mu, eta, so this is, what is the equation of wave in 2 dimension?
One over v squared utt equals to uxx. Or is it? I don't know if the constant is right.
And in this wave equation, this constant is taken to be whole constant. Why it is so? I already have given you the explanation behind this. Like if you remember about the advection equation. So how the advection equation came? This operator was operating on. And what was the solution of this advection equation? What was the solution of this advection equation? It was constant along the characteristic dx over dt when the characteristic is a constant straight line, is not it?
Also, you can derive the wave equation via the Maxwell equations.
You can, but I am just repeating why we call it a wave equation, because its solution was a wave whose amplitude was not changing with time, only it was transmitting an information with a distance c of t. Do you remember the theory which how I explained this? So every time you told me that you are not sure whether this c is a constant or not, but if you remember the theory of advection equation, then you will be sure that the solution of the solution of the advection equation is a wave which is transferring information, which is transmitting an information with a fixed distance c of t. So that's why this c has to be constant, then its solution will be wave. And if this c is not constant, in that case we cannot write it in this way, and we are going to get the nonlinear wave. So that's why this c is a constant. So if suppose I take c equals to 1, so this will be del 2u over del mu square plus del 2u over c equals to -1. This is the wave equation. If I am taking this c equals to -1. Now I have a question for you. If I am writing it, suppose v is any function that is coming from c naught m r2, then this will be coming. Can anyone tell me what will be this adjoint operator?
In general, it would be like a Hermitian operator.
No, just tell me exact form, not general. Just you can tell me the exact form. What will be this L dash?
It will have derivatives.
Yeah, so tell me what will be that derivative. Calculate and tell me. You just have 1 minute because it is not that much difficult if you have understand the previous theory.
I'm not sure right now.
Anyone like Camilo, Roberto, anyone can explain me what is this L dash?
Just by trial, we can use if we define L like a derivative, just one derivative, the d.
No, this is L, huh? This is the double derivative. I think, I don't know, you are understanding the previous thing which I am explaining or not. So, if this is omega and then del 2u over del mu square plus, say this is dx equals to d mu d eta. This dx is d mu d eta because this is a volume integral. X equals to mu comma eta. This v is vanishing, v equals to 0 on delta omega, where omega is contained in r square. So this will be omega del 2 u over del mu square v dx plus omega del 2 u over del eta square v. If this derivative will pass to this v, then what it will be? -1 to the power 2, because this is the second order derivative, omega u del 2 v over del mu square dx. Is it clear how I am writing this?
Yeah.
-1 to the power 2 is 1. So this is L dash. And what was our L? L was, can anyone tell me what is L?
The second derivative with respect to mu plus the second derivative with respect to eta n. Right?
Yeah. So what is the difference? What is the difference between L and L dash?
Is the same operator.
Yeah, so L equals to L dash, the adjoint operator is the same as the operator for the case of the wave equation.
Yeah, because we are working with real phenomena, so we have our mission.
No, that is not a reason.
Oh yes, you're right.
The reason is that in the wave equation, the coefficients are constant. The coefficients
Yes.
are not function of x and t. So when the coefficients are constant and here you can see that the coefficients also appear. That's why that operator is different. If those coefficients are constant, then you can simply write here in the same fashion. And then this is a self-adjoint operator. So the operator L dash in the case of the wave equation is same as the operator. The adjoint operator in the case of the wave equation is the same as the operator. So that's why it is called self-adjoint. Okay, I would like to ask you one question. Was this clear to you or not? This thing? Or shall I explain it again? Because this derivative is very important. I don't know why you could not relate. Shall I explain it again? This theory?
But more than constants, they have to be real functions.
That's why I'm taking in Rn now, because we are talking about the real phenomena. I am not talking about the real function. I am talking about how I am passing this derivative to the second function. Is it clear?
In the operator sense, yes.
In the operator sense or in general sense, when at least one of the function vanishes on the boundary, is it clear or not? This line is
Yes.
clear or not?
Yeah.
So that was the thing. That was I was asking. So if that's, I am doing the same thing. Why, I don't know why you could not tell me. So for the wave equation, the adjoint operator is the same operator. That's why it is called a self-adjoint. So there is an example. I am not explaining this thing in a detail. I have just written this is self-adjoint. So I have given a function, and that function is going to be solution, and it has infinite solution, like more than one solution. So you can take a look. I'm not going to explain. The main point was the self-adjoint. If it is clear, then it is fine. We can proceed. Now I am going to talk about the distribution solution. So this was the example which I discussed, self-adjoint. I haven't explained. So this u meta comma n is basically del 2u over del mu square plus del 2u over del eta square, because I am taking the coordinate in two-dimensional mu comma eta. It was just a bookish notation. Yeah. So I have already uploaded the notes. So sometimes if you get confused, you can have a look at the note. So can anyone tell me what is the Heaviside function on unit step function?
0 for x less than 0 and 1 for x positive, greater than 0.
And what is the derivative of this function?
The delta, Dirac delta.
What is the Dirac delta function?
Infinity on x equals to 0 and 0 in all of the otherwise.
Yeah, otherwise when x is not equals to 0. So this is not a very real function, like we call the Heaviside function is not a real function. This function has been self-made function and it is used in a lot of theory. That's why this function has been defined, because There are a lot of if you go for 1 over 1 minus x, so like not this exactly. This can be written in the term of Dirac delta function. This gives us 1 over x. This can be written in the term of the Dirac delta function. So there are different kind of use that of the Dirac delta function, and mostly it used when we are talking about the flow in a circuit. Yeah, flow in a circuit. Mostly, I think a lot of electrical engineer problems can be formulated in the Dirac delta function. Am I right? When there a pulse comes and the pulse becomes infinity. A pulse comes
Yes.
and it becomes infinity.
Also, yeah, that I was having like a problems with the primitive, well, the anti-derivative of the uh, delta function. Like that's not even that's a distribution, right? So the derivative is like a cumulative distribution. Yeah.
Yeah, so basically we are going to see that. I did not know that you guys already know about that. If you already know about that, then I can proceed. I can draw. But if you want, then I can discuss the same thing which you are telling me. So actually, I was going through the solution of the Laplace equation, and then I got to know that I need to define the solution in the terms of the kernel. So and I also, in your syllabus there are a problem like electrostatics. So there are some examples, and to discuss those problems I have to define this distribution. So that's why I just defined this thing. So if at some points you feel that you already know, so just say me, don't do this, we can do that.
I don't know. I don't know about the topic. I just know like the identities.
Yeah, that identity I'm going to give you proof of those identities.
I don't know anything about the theory of distributions.
Yeah, so I am going to give the proof how. Have you seen that what is happening here? This operator is distributing on the second function. This operator is distributing on the second function under this integral. So now we are going to do the same thing for the Heaviside function, and then if this u is a Heaviside function, then what will be LH? This will be a delta function, because the derivative of the Heaviside function is the delta function. So I am just going to give you the distribution theory. I am going to give the proof. So consider this Heaviside function. This is a very basic thing, and some of you might be knowing of that and some of you might not be knowing of that. And most important thing, when we define the Heaviside function only in one dimensional, when it is defined on the real variable in one dimensional, then its derivative is the Dirac delta function. So be very careful. Its derivative is Dirac delta function in one dimensional. In another dimension, we don't know. So this Heaviside function is a C1 function or not? This function is C1 or not? Is it differentiable?
Not at every point, right?
Exactly. So this function is not C1. So its total derivative is not possible. However, we can derive its weak derivative. So this H is not certainly. You guys already know a lot of things, but if it had a weak derivative H dash s, then what was the definition of the weak derivative? Yeah, so u, the derivative of u is called the weak derivative if it satisfies this equation. If it satisfies this equation for any compact support v for any v function which is a C1 function and vanishes on the boundary, then equation 6 suggests that we use formal integration by parts. So h dash x should satisfy integration from minus infinite to plus infinite h dash x v of x dx. So this is the first order derivative. Now we already know the derivative defined in the previous thing. So this will be minus infinity to plus infinity hx v dash x d of x. So since we are in one dimensional, we are in one dimension and this is the first order derivative. So since the first order derivative, just let me write it in the correct way. The integration of this function, take it as a first function and it is a second function. This is the last time I am explaining it. After that, I will already assume that you guys are aware of these things. So the first function and the integration of the second function is as it is. And we are assuming that these functions are defined on the boundary and this v vanishes on the boundary. So using the Gauss divergence theorem, it will be delta r v h d of s. And if any of these vanishes on the boundary, so this integral will be 0 and minus infinite to plus infinite, the derivative of this function del v over del x and the integration of this function h of x dx. So this got vanishes and we are left with minus infinity to plus infinity del v over del x, that is v dash and hx dx. If you have doubt, then please do ask. So now the Heaviside function is 0 when x is less than 0. However, it is 1 when x is greater than or equals to 0. So minus 0 to infinite hx is 1 v dash x dx, and for minus infinity to 0 it is 0. So the second term will be 0 and the integration of the derivative function is the function itself from 0 to infinite minus. So minus v infinite plus v of 0. Now we have assumed that what is the boundary of R? The boundary of R is minus infinity and plus infinity and v vanishes on its boundary. So v of infinite is going to be 0 and we are left with v0 for all v belonging to C01 R. Since h dash x equals to 0 for x not equals to 0, this suggests that h dash 0 should be infinite, and that is also the derivative of the delta function in such a way that integration of h dash x vx dx equals to v0. Now we know that no two functions behave like this. So we call it a generalized function or distribution. We can also process taking more derivative. We can also process taking more derivative. So let's talk about the nth order derivative or second order. So integration minus infinite to plus infinite h double dash x vs dx is equals to minus infinite to plus infinite hx v double dash x dx, and that is equals to 0 to infinite v double dash x dx is equals to v dash x 0 to infinite. At infinite its value is 0 and that's 0, 0, so minus v dash 0. Provided v is sufficiently smooth, it means the derivative which is passing to the second function, that function should be that order of that differentiability. So if there are third derivative, so we should be third order differentiable, smooth and has compact support. And simply we take that this V is belonging to C naught infinite over R. This kind of differentiation is called, this is called distributional differentiation, and the functions in C naught infinite R are called test function. So basically this V is also defined here as test function, and also this V was defined as a test function when we were talking about the weak solution of the first order partial differential equation, first order Cauchy linear partial differential equation. Now since we know that h dash x is equals to delta function, so the delta distribution to be the object delta x, so that formally integration of Rn delta x vs dx equals to v0 for every test function v belongs to C naught infinity Rn in the one dimensional case. We know that this delta function is nothing but the Heaviside derivative of the Heaviside function. Now comes to this function define delta mu of x is equals to delta x minus mu, so that a change of variables y equals to x minus mu gives integration Rn delta mu x dx dx is equals to integration of Rn delta of x minus mu v of x dx. Under this operation, dx will be dy and x will be y plus mu. So, when we calculate this integral, earlier it used to be if v of x dx, so it used to be v of 0. Now mu is here, so it will be mu of v of mu. So, we can see that here we can see that, here we can see that we have defined the delta function and its directional and its distributional derivative with the help of this test function. And also we can see that this distributional derivative is giving us a single value. It is a single value. V of mu is a single value, that is a constant value for every mu.
Yeah.
So I don't think I should write. I can explain it via notes. So we have defined the delta function and its distributional derivative through their action on the test function. So what we have defined, delta of x minus mu v of x ds, x minus mu, ds is equals to v of mu, and this is a single value, and this is the action of the delta function through a test function. So we have defined the delta function and its distributional derivatives through their action on a test function, because this v is a test function. A distribution assigned to every function v a number. This is a number because this is a single value. Also this action is linear. So if you will calculate delta operating on the linear combination of two test function alpha v plus beta w. So if this is a delta function and we are taking, suppose this is delta x, we are taking two test function v and w. So it can be written as since here is no mu, x minus 0, so this will be alpha of v of 0 plus beta of w of 0, and this is nothing but alpha of integration delta with so this function is also a linear function. And similarly for the derivatives of delta and delta mu, this function is linear for delta 0 and even for the delta mu. For delta mu it will be assigning a value mu, and for 0 it is assigning the value 0. So therefore a distribution should simply be thought of as a linear mapping from C naught infinity Rn to R, because it is taking a single number. So that's why it is a mapping. If you are taking a delta function in Rn and with this test function that is also smooth in Rn, then it is assigning a linear mapping from the n-dimensional space to a number, that is from an n-dimensional space to R. If you have any doubt in this simple derivation, then you can ask. So a distribution f in omega is a linear mapping from C naught infinity omega to R, such that at any sequence this f vanishes for every sequence with support in a fixed compact set K, and whose derivative is tending to zero uniformly in K as J tends to infinity. If F and Fj are distribution in omega, then Fj is approaching to F as distribution provided that Fj for every test function is also approaching to f of v for every test function v. The support of a distribution f in omega is the smallest closed set k, such that f of v equals to 0 when v equals to 0 in a neighborhood of k. So this is the definition which is derived, like which has been written using the above derivation. Next we are coming to the definition of our interest. That was not of our interest. We are just going to use that result. So, actually, we are very interested in finding out what is this partial differential equation? What is the name of this partial differential equation? When L is a wave operator, when L is a Laplace operator,
Poisson, I think, the Poisson equation.
Poisson equation, yeah, exactly. So this is Poisson equation. So we are going to see the solution of the Poisson equation in the next section. That's why I am making this kind of food here. So we are going to talk about the solution of the Poisson equation. We can also talk about the solution of the heat equation. So this theory is very useful in the solution of the Poisson equation, and also in the heat equation there is a Duhamel theory. So we are going to use this theory. So that is the reason why we are studying these things. So distributions U and F satisfy LUF in omega, where L is any operator. L can be wave operator. If it is a wave operator, then it is a self-adjoint. It is a self-adjoint operator. It may be Laplace operator. In the case of Laplace operator, it is again going to be self-adjoint operator. It can be heat equation. In heat equation, we are not sure. We can see that in the sense of distributions, U is a distribution solution of LU equals to F if L dash V is equals to F comma V for all V belongs to C naught infinite omega. So this U and F satisfy this equation, this linear partial differential equation omega in the sense of distribution. So U is called the solution of this differential equation if this satisfies this. So what is this? This is integration U L dash V dx omega is equals to V L of U dx omega, and L of U is nothing but F, so we can write F of U dx. So since this is defined, this inner product is defined in this way, so this inner product is this way. So if this distribution can be written for U, if this distribution can be written for U under any test function V, this distribution can be written for U, how to say it, if we can write this distribution for all compact support V or for all test function V for the given U, then we call U is a distribution solution of this linear partial differential equation, where this linear partial differential equation is of mth order. So in such way, L is defined as modulus of alpha A alpha x d modulus of alpha. So this is the operator. Now this was the way how we are defining the distribution solution. So U to be a distribution solution, what is the necessity? At least U should be integrable. What was the necessity of U? U should be integrable. Is this definition clear? In particular, if U is belonging to L1 local omega, so if U is locally integrable, if U belonging to L1 local, if U is locally integrable, then it is a weak solution of L of U equals to F, then it is a distribution solution, and the condition U comma L dash V F comma V may be expressed in distributional integral notation to obtain integration omega U L dash V dx equals to integration omega F of V dx. Please tell me whether this definition is clear or not. Another, I can explain it again and again unless until it will be clear to all of you.
Yeah, it's clear.
Okay, I don't know why, but Kapila's voice is coming very slow. Next, we are going to talk about the convolutions and the fundamental solutions. So the most important thing which is of our interest is fundamental solution. I don't think I will be able to reach to that topic, but I will take your 5 minutes extra just to explain the convolution. Do you know that in the Green's kernel we use the convolution theory? You have idea, in the Green's kernel we use the convolution.
I didn't notice.
Okay, so don't worry. Just tell Roberto and Yvonne, just tell me till this topic everything is clear how we are writing the definition, how we are deriving the things.
Yes.
Okay, then fine. Because this is the very basic thing. In the advanced, we are going to just use this thing and I am not going to explain it. So, if you have even small doubts, you will have today and you can read, then you can ask me. The convolution of two functions f and g that are defined on Rn is a new function h defined on Rn, and how this is defined. So the convolution of two functions is f x minus y z y. This is the convolution product. So this is your equation number 11. Assuming the integral converges, assuming the integral converges. For example, if suppose this small f and g locally integrable, even in that sense we can define this convolution. Even if f and g are locally integrable, even if f comma z is belonging to L local 1 Rn and at least one has compact support, then 11 converges and f star g is well defined, and a change of variables z equals to x minus y, so that if you will take a change of variable x minus y equals to z, then dy will be dx x minus y equals to z, so f of z, g of x minus z and d of x. Yeah, and in that case we can write it f star z, so that f star z equals to z star f. So convolution is commutative. So this was the property of the convolution. Now I am going to show the distribution of this convolution, and this is not, I will not discuss it today. Again, it is a one page long topic, so it is going to take again minutes. So I would like to ask you to do two things. First things, please, it is my request, please read what is the adjoint operator and what is the operator, how I am defining this operator L and how I am defining its adjoint operator when I am calling it a self-adjoint. And the second thing, what is the meaning of the convergence of this convolution. So this is the three things which you will study, and if you get any kind of doubt, then you can ask me tomorrow. Is it clear what you have to study?
Yes.
Okay, so please study the operator L, its adjoint. When it is self-adjoint, what is the convolution, how it is defined, the convolution is commutative, and also how the convolution converges. So what is the meaning of these notations? Please do read, and tomorrow we are going to talk about the solution of the non-homogeneous equation. In particular, you can say that we are going to talk about the solution of the Poisson equation, and that is known as the fundamental solution of L. So we will not especially mention that the solution of the Poisson equation. So basically, what is our aim to discuss tomorrow? Firstly, let's memorize to all of you what we have talked today. We have operator, adjoint operator, and then we have self-adjoint. Then we have studied the Heaviside function. Then we have studied the delta function. Then we have defined the weak derivative of the Heaviside function. Weak derivative of the Heaviside function, and since this Heaviside function is not a real or a true function, so that's why we are defining its weak derivative, because its derivative is not going to exist in the whole domain. And then after that we have defined the distributional derivative, or we can say that we have defined the distributional solution of L of u equals to f. Now tomorrow our aim is to find out the solution of this non-homogeneous equation, and we we are going to talk about the fundamental solution of this non-homogeneous equation. So this is our aim to discuss tomorrow, and if time allows us, then we are also going to discuss the theorem. I don't remember the name of the theorem. Yeah, then we are also going to discuss one real life phenomena, electrostatics. So this is the topic in your syllabus. So in your syllabus, you have to study 3 real life phenomena. Let me open the syllabus. So electrostatics and the use of the elliptic equation in membranes. So tomorrow most probably we will try to understand what is the electrostatics, how we are writing its fundamental solution using this delta function or using this fundamental solution theorem. So this is a very important and very famous like electrostatics. So we will formulate the system and then we will try to write the solution of the system. So here we are done with a lot of things. Now I am aiming like in every class I want to solve different kind of things like Dirichlet. We have solved one Dirichlet problem where it was homogeneous and the solution was defined on the boundary and the boundary was rectangle. Tomorrow, if like in this week, I would like to ask the solution of the Laplace equation using the Dirichlet boundary condition, but the boundary will not be a rectangle, rather than the boundary will be a circle. So Dirichlet problem on a sphere, or you can say on a ring. So we will also try to solve a question to understand how the things are coming, okay? And if you guys get time, so you can take a look so we can discuss. So this unit 3 is very interesting, like everything is very easy, not very geometrical like the first or second unit. Roberto, are you getting the things which I am explaining here? Are you getting the things which I am explaining like this topic? Okay, so when you take a look at the notes, so is it clear to you? Sorry, when you study the notes, so is it clear to you or not? When you take a look at the notes which I am uploading in the Google Classroom, the handwritten notes which I am uploading in the Google Classroom. So after taking this class, when you study those notes, so things get clear to you or not? Um, can anyone explain in Spanish what I am saying?
Que si cuando revisas las notas entiendes.
Okay, so please take a look at the notes. Then it will be more clear to you because sometimes I am explaining, so it might be difficult. So go through the notes. Everything is written there. Yeah. So see you tomorrow. Yeah. Bye. Yeah. Bye.
Okay, bye.